Hi, I'm Bob. Welcome back to 5 Minute Econometrics. Today we will explore how to test for heteroskedasticity. We will learn a test that can tell us whether the variance of the error term in the model is non-constant. The test is known as the Breusch-Pagan test or the BP test. BP test stands for Breusch-Pagan test. It is used to test whether the model exhibits heteroskedasticity, that is, the error variance is not constant. The idea behind the BP test is that if the error term has constant variance, that constant variance should not change with the explanatory variables in the model. If we find strong evidence that the error variance is a linear function of the explanatory variables, indicating that the variance changes with the explanatory variables, then the model is very likely to suffer from heteroskedasticity. We know that the OLS residual is an estimate for the error term. The squared OLS residual is an estimate of the variance of the error term under the zero conditional mean assumption. Thus, we can construct a new variable equal to the squared residuals from the OLS regression and test whether it is correlated with the explanatory variables in the model. In mathematical terms, for a multiple linear model, the null hypothesis of the BP test is the homoskedasticity assumption, that is, the error variance is constant, while the alternative hypothesis is a violation of the homoskedasticity assumption. We write down the definition formula for the variance. Because of the zero conditional mean assumption, the second term is 0. We can simplify the error variance into the expected value of the squared error. So, the null hypothesis of homoskedasticity is equivalent to the following hypothesis. It implies that the square of the error term is not correlated to any of the explanatory variables in the model. For the linear model with the squared error term as the outcome variable, the null hypothesis is equivalent to all coefficients in the model being 0. Since the OLS residual mu hat is an estimate of the error term mu, we can estimate the model with mu hat squared as its outcome variable. If we fail to reject the null hypothesis of homoskedasticity at a sufficiently small significance level, we typically conclude that heteroskedasticity is not an issue. However, if we reject the null hypothesis, we should be aware that the model may be affected by heteroskedasticity. There are 2 steps to do the BP test. In the first step, we estimate the model using the OLS method and store the residuals. We then construct another new variable equal to the squares of the residuals. In the second step, we run an auxiliary regression. We regress the squared OLS residuals on all the explanatory variables. Then we compute the LM statistic for the joint significance of the explanatory variables. The LM statistic equals the sample size times the R squared from the auxiliary regression. Under the null hypothesis, the LM statistic is asymptotically distributed as a chi-squared distribution. When the outcome variable is a positive continuous variable, we often use its logarithm. The coefficients can be interpreted as the percentage change in the outcome variable for a 1 unit increase in the explanatory variable. In addition to this desirable interpretation in economics, heteroskedasticity is often reduced when we replace the level functional form of the outcome variable with the logarithmic functional form. We will compare these two models using the BP test. The models use years of education, age, number of children, gender, and other demographic characteristics to explain hourly wages. I will compare the logarithmic form of the hourly wage and the level form of the hourly wage as the outcome variable and examine which model exhibits heteroskedasticity. We first estimate the model with log hourly wage as the outcome variable. In Stata, the predict command with the residuals option stores the OLS residuals in a new variable. I name it mu hat. I then generate a new variable equal to the square of mu hat. Finally, the squared mu hat is regressed on all explanatory variables. The LM statistic equals the sample size times the R squared, which equals 21.56 in our example. Its p-value is 0.158. We fail to reject the null hypothesis of homoskedasticity at conventional significance levels like 1%, 5%, or 10%. There is no heteroskedasticity issue in the model when we use the logarithmic form of the hourly wage as the outcome variable. Next, we estimate the model with the level form of hourly wage as the outcome variable and follow the two steps to do the BP test again. The LM statistic equals 260 and the p-value is 0. It is strong evidence against the null hypothesis of homoskedasticity, and the model is subject to heteroskedasticity. Today, we conducted the Breusch-Pagan BP test for heteroskedasticity on two models. We found that the model with hourly wage as its outcome variable exhibits heteroskedasticity, while the model using the logarithm of hourly wage does not. This observation confirms that using logarithmic functional form usually helps to alleviate heteroskedasticity. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.